So I'm starting with a question, namely, why do we study mathematics? So all those who are present I would like them to write something in their chat box. Why do you think you study mathematics? Just write one or two reasons why you study, and Amya will give me a feedback. What are your answers? Amya, as soon as you get 3 or 4 responses, please let me know so that I can go ahead.
Yes, sir. Someone said understanding numbers, use it in our daily lives for better problem solving skills, to develop an analytical mind.
Great.
Yeah,
right.
Basically these are the responses so far.
Good responses, I would say. So normally when I do a session with students, I ask this question, and this is the answer I get. I get the answer that we study mathematics for examinations. Because it is in the syllabus, we have to study it, so that's why, that's the reason we study. Okay. Of course, we study for examinations because that is part of our curriculum, that is part of our education. But there is something more. We use it for calculations, for applications, and much more important is for developing our inner capabilities. This is very important aspect of learning mathematics, learning how do we do mathematics. And this is one of the answers provided by a mathematician called George Polya. George Polya, when he was asked what are the aims of education, he said one aim is the lower aim, enabling people to take up good jobs or become a good member of the society and so on. And but the second more important thing is the higher level aim of education is developing the inner capabilities. What does that mean? That means analyzing things logically, reasonably, and making logical conclusions from those assumptions that you make and apply them in the real life. So that is what developing inner capabilities means. Of course, we use it for exams, right? So, Amya, how many participants have joined?
So there are 89 participants.
39.
89.
89. Good. Okay. Thank you. So let me. And this is a very normal question, and every student asks normally is when we will ever use this in the real world. So we'll try to answer some of these questions. So this is the title of my presentation, Discovering Mathematics from the Real World to the Mathematics World. So where is mathematics? So let us begin with a problem called the math birthday. This is the birthday problem. So I'm going to ask you, let us begin by calculating your birthday number. So what is the birthday number? So everybody in the audience will note down their date of birth. For example, if you are born on 26 January, then we are looking at the number 26. That is your birthday number. Okay. So please, I think all of you remember your date of birth, not the year. I'm not interested, not the month. I'm just interested in the number. It's 26 January, right? So here is the claim that there are at least 2 persons in the audience. Of course, we are not in a hall, but in the digital hall, which has the same birthday number. So let us verify. So please write down your birthday number in the chat box, and Amya will have a look at it and verify the claim that at least 2 of them have the same birthday number.
Yes, sir. We got 26 and 25 as common. 15 is common. 25 is common. 3 is the date. 16, there are 2 people having birthdays on 16.
So thank you, Amya. So we have already verified the claim without doing anything. Okay, essentially that this is true. that there are two persons, at least two persons in the hall, in the audience, in those who are present, that they have the same birthday number. I can extend this game a bit more, but let me not do that. Okay, so there is. So what is the reason for that? Why I made a claim and everybody was, when they wrote down, we were able to verify that it is true. This is based on something called in mathematics. Here is the mathematics entering into picture. Something called a pigeonhole principle. So what does this principle say? It says if there are 10 pigeons and they are put in 9 holes and no hole remains vacant, then what should happen? Right? So all of you can think about it. If there are 10 pigeons, 9 holes, and all of the pigeons have to go somewhere to the holes. That means at least, for example, here in this hole, there must be 2 pigeons. So at least one hole should have 2 pigeons, right? So this is called, classically, this was called the pigeonhole principle. And why it is called a principle? Well, you don't have to verify it. Something which is principle is it is accepted as a true thing in mathematics. So no proof is given for that. So a mathematical version of this is the following. If m pigeons are put, pigeons are put in m holes, now here is a version of it. Number of pigeons and number of holes is same, then there is an empty hole. If and only if there is more than one pigeon in a hole. So if number of pigeons and holes are same, then the only way a hole can remain. Amina, are you able to see my screen or not?
Yes, sir.
You are able to see the screen, na?
Yes, yes.
I was just wondering, people are seeing my face only, or the important thing is the screen?
Yeah.
Okay. So pigeonhole principle is one way of writing the pigeonhole principle is if m pigeons are put in m holes, the number of holes and pigeons are same, then there is at least one hole which is vacant if and only if one hole will be empty. If and only if this is if and only if statement, there is mathematical thinking coming. This statement, empty hole, if and only if there is a hole with more than one pigeon. Another way of stating the same thing is if there are m pigeons are put in n holes, m pigeons in n holes, and m is bigger than n. That is what we saw in that illustration, 10 pigeons in 9 holes. Then there is at least one hole with more than one pigeon. That is another version of the pigeonhole principle. This pigeonhole principle has a lot of applications in mathematics. Since all of you are internet savvy, go to the Google and when you are free, look for pigeonhole principle and its applications. There are many applications of this, a lot of them. So here is a very simple one, which we come across almost every day. When we go to the bank and we want to withdraw money, say we want to withdraw 1,000 rupees, and then or 10,000 rupees, some big amount, then the cashier will give us a bundle of notes, say 100 rupee notes, 100 notes. So in that bundle, he checks it in the machine and says there are 100 notes. So this is your money, you take it. And then you count it and you find it there are only 99. So you give it back to the cashier and say that in the bundle there are only 99 notes, one is missing. He counts again and says there are 100. Now, you see, here is a dilemma that in the bundle, the number of notes is there. Physically, we know how many are there, right? So that cannot be changed. That is there. Only thing is there is a problem in counting, right? So either the cashier is making a mistake or I am making a mistake. So the pigeonhole principle says that that process of counting should give you a unique number. So essentially that says when you take a set and try to count its number of elements, if the counting stops, right? if there is a 1-1 onto map between the set and the numbers 1, 2, 3 up to n, then there will be only a unique n that you will get, which will give you a 1-1 onto map from that set to the natural numbers 1, 2, 2 up to n. And that will say that this set has got finite number of elements and the number is n. So this pigeonhole principle assigns to every set either a number, natural number, if it is, we will say that is a finite set. Otherwise, you can't, your counting goes on and we say that is an infinite set. So this is an application of the pigeonhole principle. So this is something which is common, and you might have already seen some applications of in chemistry, for example, if you're looking at calcium and H3PO4 hydrophosphoric acid, if they combine, it gives you calcium phosphate and hydrogen comes out, right? So the problem is how much of calcium interacts with how much of acid to give you how much of phosphate and how much hydrogen comes out. So the principle is whatever you've taken, that is only change the form, that cannot be destroyed. So that is what is called balancing the equation. So if you, this is how one can do it, that U times calcium plus V times phosphoric acid, gamma times this many moles, give out delta times H2. So if you write U, V, gamma and delta, and then you have to balance out these equations. That means number of calcium on both sides should be same, number of hydrogen on both sides should be same, and so on, right? So that gives you some kind of equations. U is equal to 3 gamma and this equal to this. So this is what is called a system of linear equations, and you have to solve this system of linear equations in U, V, B, and gamma and delta to find out what is the value. So once you solve it, so you get these values. So system of linear equations, some of you who are 11th and 12th would have gone through solving system of linear equations. So that is useful in solving chemistry problems. And something similar comes in physics when you're trying to study electrical networks. So let me skip this example. Again, my electrical networks is balancing the equation. So how much current is flowing, what is the voltage drop across the nodes. So using Ohm's laws and Kirchhoff laws, you can solve. So you get the system of linear equations and you solve it. I'm just going fast through this. You can try to do it later on after looking at the video. Okay. So mathematically, the problem is to find out the values and so on. That can be done by looking at system of linear equations. Mathematics language is used because it is not ambiguous compared to the verbal expressions. So let me now come down to very basic kind of examples. I just gave you a glimpse of how mathematics comes across our life and how do we use it in some parts of it. Here is something very simple and interesting, mathematics from kitchen to the conics. So I will go a bit slow here. So here is pressure cooker, which almost all of you must have seen in your homes, and probably nowadays in the lockdown situation, you might be using it also, trying to learn cooking, right? So let me show you something about these pressure cookers. One is Hawkins, other is Prestige. These are some of the popular ones which are used. So let us look at it. So here is the question I'm putting in front of you. So please try to write an answer in your chat box. What are the similarities and differences between the two designs? One is from a brand called Hawkins, other is called Prestige. Please try to write in your chat box. Similarities probably, I think we can all know what are similarities. These are gadgets that help us to cook faster things and both work under the increased pressure in the reduces the boiling points, the faster cooking and so on. So let us look at the differences between the two. So please try to write down one or two differences that you think are important that distinguishes Hawkins pressure cooker from Prestige. And Amya will keep an eye on the chat box and tell me one or two inputs so that we can take the discussion. So take 2 minutes to write down what you think is the difference or the differences between the two pressure cookers.
So the participants have written that the volumes of the cooker are different, might be different.
Okay.
The shape, of course, is different.
Okay.
The width is different.
Okay.
The height of the cookers might be different.
Good.
The height, the depth of the cooker is different.
Okay. Good.
The material used might be different.
That's okay. Good.
Shape of the lid is different, so that might add to the volume.
Okay. Right. So let us go over to something that the last comment saying that the shape of the lids are different. So that is a very important difference in the designs. Volume is different. That may be in the picture. This may Hawkins may look smaller. This may look bigger. That is possibility, right? But in the design part of it, I looked at two designs, right? Not the attributes of the thing. So design, there is a very critical difference, crucial difference between the design of the top of the pressure cooker in Hawkins and the top of the Prestige pressure cooker. So let us look at one by one these things and try to understand what is the difference. You might have already looked at the physical difference. In the Prestige, you put the lid at some lid is first of all the lid is outside the pressure cooker, the body of the pressure cooker. One, and secondly, you put it at a particular angle and then you slide it towards this handle, and then it gets locked. While in the Hawkins pressure cooker, you have to dip this part of the top, the top of the pressure cooker. You have to rotate it at 90 degrees and put it inside and then rotate back, make it flat and then lock it at this end. So there is a difference in locking systems. One is outside locking, one is inside locking the pressure. So let us look at, here is a picture of the Prestige pressure cooker. If you look at from the top, the Prestige cooker looks like this, right? It looks, you can see everything in the pressure cooker, okay? And let us try to analyze it a bit mathematically. See, you might have noticed already that the top opening of this pressure cooker is a perfect circle. The top opening is a perfect circle. Right? The pressure cooker looks like a cylinder, a right circular cylinder. The bottom is same as the top of it. Okay, and let us try to verify this. I am going to use a software called GeoGebra, which some of you might be already knowing it. If not knowing it, it's a very good tool to analyze mathematics. Okay, so here is the GeoGebra. Okay, so it comes with a panel called algebraic panel, comes with a geometric panel. So what I've done is, when I click at show pressure cooker, this is a pressure cooker picture I have taken in my kitchen and brought it in GeoGebra. Right? Now I want to analyze whether this is a circle or not, is perfectly circle or not. So here comes our knowledge of a circle, that if I take 3 points, then there is a unique circle passing through them. Right? Given 3 points in the plane, there is one and only one circle that will pass through it. So let me choose 3 points on the opening. So here are the 3 points C, D, and E, which I have taken on the top opening of the pressure cooker. And now what I'm going to do is I'm going to fit a curve through this, right? So here is the curve through this. So this red one, you see it here, is the curve passing through these 3 points. And what is the equation of this red one? Here you can see the equation is x minus 4.38 square plus y minus 9.89 square is equal to 25.99. That says that is x minus a square plus y minus b square equal to r square. So this is the perfect circle. So the top opening of the pressure cooker in the press stage is a circle, right? So let us analyze something similar for the Hawkins pressure cooker. Here is the Hawkins pressure cooker. I have done the same thing. I have tried to bring in a picture of the Hawkins pressure cooker into the GeoGebra panel. So here is the GeoGebra panel. Right? Okay. So let me hide this also. So here is the pressure cooker. Okay. Now, if you try to see the opening here at the top, you can already make out that this opening seems to be bigger than the perpendicular opening here, right? So this is not, it does not look like a circle. A physical observation, it says that the opening of the Hawkins pressure cooker is not circular. So let us take 3 points. So these are 3 points. And if I try to pass a circle through these 3 points, so this is the circle passing through these 3 points on the rim. And you can already see that it does not fit the rim, right? It is not fitting the rim properly. So what do? I want to fit a curve which perfectly sort of fits. So let me avoid the circle now. Circle is not doing a good job. So let us take some more points. Our data increases. So now what I'm doing is I'm increasing the data available to me, and I'm trying to fit a curve through now 6 points. So C, D, E, and E were the earlier points, and now there are F, G, and H. I've taken 3 more points. I'm trying to fit a curve fitting. I'm doing a curve fitting, a curve which passes through this, and this is the curve that passes through it, the green one. So you can see that green one is, well, exactly fitting. At least in this case, it seems to be exactly fitting. And what is this green curve? If I look at it, this is the green curve. That doesn't, can you recognize what is this? GeoGebra says it is an ellipse. There is an ellipse passing through these points. Okay. So let us see if we can recognize this ellipse in the form of, no, it won't give it. Okay, fine, doesn't matter. So what I've done is I've fitted a curve, and an ellipse fits perfectly well in my. So how does this help? This part of the opening is bigger than this part of the opening. This part is smaller. So, but our handle, the top lid of the pressure cooker, that is going to be a circle which is exactly of this red one. So that circle will have a radius slightly bigger than the major axis of the bigger axis of the ellipse. So once I do that, so that lid, I will tilt it, put it inside, rotate it, make it flat. So what will happen is, because opening is elliptical, but the lid is circular, which is slightly bigger than the major and the minor axis, it will fit in nicely from the inside and lock it up. So observing the top of the pressure cooker gives me knowledge about two things. There is something called a circle and there is something called an ellipse. What are these two curves, right? So let us take off from there and try to analyze something called conic sections, right? The circle and ellipse are parts of parts of a cone essentially. So how do you get that? So for example, if this is a cone, this is a picture, if you cut it by a plane which is perpendicular to the axis, what you will get is a circular object. The base will be a circular, it will be a circular cone. Like the cone you have got, it's a smaller part of it. But if you cut it at an angle, like the plane is at an angle, then you will get an ellipse, right? And if you cut it some other angle, right, we'll see what are those angles, then you'll get a hyperparabola. And and if the cone is the two upper and lower, there is a cone upper and lower, and you cut it, you get what is called a hyperbola, two parts of the hyperbola. So let me just go through this small animation to show you. Either way, this cone is a surface of revolution. Revolve is stick, you will get a circular So this is the names of cone, vertex, axis. This is called the upper part or upper mapping. This is the lower part. This is called the lower mapping. And now we are going to cut the plane, cut the cone slice by a plane which is perpendicular to the axis. And you get a circle. At an angle, you will get an ellipse and a parabola or a hyperbola. This is the angle I was mentioning. This angle is less than 90 degrees. Or it is equal to 90 degrees. Then you get a plane. It's 90. Get a circle. And if the angle is bigger than 90, but less than alpha, this angle. So if this relation is satisfied, you will get an ellipse. And when it goes beyond that, here is alpha, here is beta. When alpha is equal to beta, you will get a parabola. And when it becomes bigger, when alpha is less than beta, alpha is bigger than beta, you get two parts, and that is a parabola. So these curves are called conic sections because they are sections of a cone obtained by slicing a cone by a plane at different angles. And these are useful in though circle is used almost every day by us in one form, all the wheels are circular, almost everything. And effectively, the gears are circular. All the astronomical bodies move in paths which are elliptical. They revolve around the sun in elliptical orbits. Parabola is useful in analyzing, for example, effects or in cricket. All shots hit by criminals are parabola. Hyperbolas, you don't see them very often in our real life, but they are used in sonic booms and so on. So, beginning with pressure cooker, we have seen what are conics and what are applications of conics, right? Conic sections. Of course, you can do it with the help of GeoGebra. So let me not go to GeoGebra applet now and just say that you can do it with the GeoGebra applet also. You can generate conic sections. So this is a physical way of generating the conic sections. But normally in textbooks, you will find equations of conic sections. Circle is x minus a square plus y minus b square equal to r square, center and radius. So how does these sections relate with the coordinate geometry representation? So the coordinate geometry helps you to represent 3D geometry that we see it here in terms of algebra equations. So all the equations of parabola, hyperbola, or ellipse that you see in your textbooks, we just define them that way, or they are defined as locus of something moving around, right? Circle is a locus of all the points which are at a fixed distance from the center, and similarly, the parabola is defined in terms of locus, ellipse is defined in terms of locus, and so on. So how does those equations relate with the geometric representation that we have seen is not that easy to get, right? And that you should try to take it as a project to analyze how do you represent the geometric objects, sections of a cone by a plane to the equations of that. So here are the definitions that conic sections are described. Parabola, the distance from a point and a line are equal. So it is the locus of a point whose distance from a point and a line are equal. The point is fixed, the line is fixed. Ellipse is the sum of distances from 2 points is a constant. So you're given 2 points and look at all those points which are the sum of the distances from these are constant. And hyperbola, the difference, and the circle. This is something interesting which is not normally done in the class books, that is the ratio of the distance from the 2 points is a constant. So these are sum, difference, right, ratio. And all of these can be done in GeoGebra. So I have drawn them in a GeoGebra thing. For example, let me show you the circle part, probably it's interesting to see, because that is something new that you don't see it in your textbooks. So here is a definition of a circle which was given by Apollonius. So this is a point P in the coordinate plane, and these are the two fixed points A and B. Okay, and I'm going to move this point P so that the ratio of the distance AP is to PB, right? AP is to PB remains a constant, and the constant here it is this constant R. Okay, so R is 2.2 here. So let me show you the magic of GeoGebra. So here is the animation which is possible in GeoGebra. So it is the path of the particle P, the point P in the coordinate plane is the locus. And if you are very keen to see what is this locus, actually you can visualize it, the locus here. So if you want to visualize, here is the point P. So let me take the point P on this side. And there is something called trace on. So let me put the trace on and do the animation now. And you will see the circle being traced. As the ratio, keep an eye here, AP is to PB remains same as 2.2. So it is a circle. It is not a circle with radius as equal to 2.2. Center is somewhere, right? Radius is something else, but it is the locus of that So this traces out circle, and it will be interesting to find out if this ratio R is given. I give you it is a fixed number 2.2. What is the center of the circle and what is the radius of the circle? So that is a project. You can take it with you and do it later on. Okay. So this is a new definition of circle that you might have seen. Right. So these are various ways. So what we have done is we have started with our humble gadget called pressure cooker, and started from there we have come to conics, and that we find in our textbook. So this is what I call it, from the real world to the classroom world. So here is the second application. I don't think I will have much time in finishing all that I wanted to say, but let me do it one more application. Who does not want to grow money? Everybody wants in this world, want to have a lot of money. And everybody wishes that there was a plant, right? We have a money plant, which is more of a decorative thing. It does not grow money, but we wish there was a plant on which the money will grow. So how do you make money grow? That is the title of my next analysis. So here is, everybody knows a safe way to grow your money is putting a fixed deposit in a bank, right? And you must have studied these things in your earlier classes, in your earlier grades. There are two ways of putting money in your bank in a deposit. One is called the simple deposit, simple with a simple interest rate, and other is a compound rate of interest. And you must have seen there in some examples that the compound rate of interest is better than the fixed one, because in the compound rate of interest you get interest on the interest that you have earned in a particular time also. So your interest generates more money for you. So that is how you grow more money, right? So here is annual rate of interest is R, P0 is the amount. Then in 1 year, your amount will grow 1 plus R. So P0 is initial. So this is the rate with which it will grow. R is the percentage, that is 5%. So it will be 5 by 100. So this is so your money will increase, will become P. Okay. At some time point, some banks started offering that will give you interest not yearly. So this is the annual rate of interest, and the interest is calculated every year. They said we'll start calculating the interest twice a year. Every 6 months we'll give you the interest. That means whatever interest you get in 6 months, that will be added to your principal, and for the remaining 6 months, that will be your new principal, and you get interest on that, right? And then some other banks said, why 6 months? We'll give you every 3 months, right? So let us assume that the interest is given 2 times a year. So year is divided into n parts, equal installments. So every month the interest is given, say 12 times. So n will be equal to 12 then. Then your principal will grow as P0 plus 1 plus R by n raised to power n. Now, supposing this n is made to increase, some bank says not only every month, we'll give you every day. So 365, n is equal to 365. Can you go on increasing this n? Can you increase n? Let n go to infinity, if that makes sense to you. So what we are looking at is a concept called limits. So which normally students study in 11th and 12th. What is the limit of this as n goes to infinity? So that will be the interest, that will be the amount that you get in 1 year. So if you want to compare, you can have a GeoGebra applet to compare. So here is n equal to 6. I can compare, for example, if I can do it in GeoGebra, but I think let me probably, since I have already clicked it, it will open it. So here is the GeoGebra applet. You can compare the interest. When n is equal to 57, you can compare the interest. So this is a simple interest, that is a compound interest yearly. This is n equal to 57. So you can see what is the difference that is making. So here is. So simple interest, this is the amount you will get. Compound interest yearly, this is the amount you will get. And if it is paid 57 times a year, this is the amount you will get. So this is possible to analyze it. So you can see the more interest you will get if it is paid more frequently. So the question is what happens mathematically when n goes to infinity? And this is a concept called limits of sequences. So this is a sequence, this is a number which depends on n. R is fixed. When n goes to infinity, this limit is equal to e raised to power r. E is a number called Euler's constant, and it is e raised to power r. So this part is slightly more mathematical, which you study in higher standards 11th or 12th. So that says that in 1 year, your principal P0 will become P0 multiplied by e raised to power r. This number e is between 2 and 3. Okay, so that is Euler's constant. So it will become much more. Okay, so this is how your money will grow. This is the growth model, and this model, when r is positive, this is the growth model for any bacteria or any species to grow. Right? So this is the basic growth model. It can be used in economics, growth of money, growth of some quantity, right, profit or something like that. In biology, it can be used for growth of some bacteria or something like that. So this is the growth model. When R is negative, that is the decay model. So this is a very useful model applicable in biology and so on. So this is how your money will grow. And this function e raised to power r is what is called the exponential function. Okay. So this is called the exponential function. So if your interest is applied continuously every moment for t years, right? Time is t. Then the model, then power t comes, and this is the model e raised to power rt. R is the rate at which something is growing, and t is the time. So this will give you a model of growth, time bound, time dependent model of growth. Okay, right. So let us go over to something more. It's a very interesting, I won't say application of it, but illustration of this, how exponential thing grows. So here is something, you take a paper, one sheet of paper, and its thickness will be something like 0.01 centimeter. Let us assume this is the 0.01 centimeter. In meters, it will be these many meters. In kilometers, it will be this one. Now, if I double this paper, I fold the paper, the thickness becomes double. So this is the thickness. From 0.01 it becomes 0.02. And this is what it happens. So I can go on folding 3 times, 4 times, 5 times. If I go on folding this paper, what do you think this happened to this thickness of the paper? Okay. You can generate an Excel sheet if you like, and it will be good exercise in statistics. Thickness 1, 2, 3, doubling it. Okay, at the third stage you're doubling it, will be 4 times, right? And so on. Double of 2 is 4, and so on. So here is a visualization of this thing, which is very dramatic. So let us visualize. See this visualization. Folding a paper.
How many times can you fold a piece of paper? Assume that one had a piece of paper that was very fine, like the kind they typically use to print the Bible. In reality, it seems like a piece of silk. To clarify these ideas, let's say you have a paper that's 1/1000th of a centimeter in thickness. That is 10 to the power of -3 centimeters, which equals 0.001 centimeters. Let's also assume that you have a big piece of paper, like a page out of the newspaper. Now, we begin to fold it in half. how many times do you think it could be folded like that? And another question. If you could fold the paper over and over as many times as you wish, say 30 times, what would you imagine the thickness of the paper would be then? Before you move on, I encourage you to actually think about a possible answer to this question. Okay, after we have folded the paper once, it is now 2/1000th of a centimeter in thickness. If we fold it in half once again, the paper would become 4/1000th of a centimeter. With every fold we make, the paper doubles in thickness. And if we continue to fold it again and again, always in half, we would confront the following situation after 10 folds. 2 to the power of 10, meaning that you multiply 2 by itself 10 times, is 1024 thousandths of a centimeter, which is a little bit over 1 centimeter. Assume we continue folding the paper in half. What would happen then? If we fold it 17 times, we'll get a thickness of 2 to the power of 17, which is 131 centimeters, and that equals just over 4 feet. If we were able to fold it 25 times, then we would get 2 to the power 25, which is 33,554 centimeters, just over 1,100 feet. That would make it almost as tall as the Empire State Building. It's worthwhile to stop here and reflect for a moment. Folding a paper in half, even a paper as fine as that of the Bible, 25 times would give us a paper almost a quarter of a mile. What do we learn? This type of growth is called exponential growth. And as you see, just by folding a paper, we can go very far, but very fast too. Summarizing, if we fold the paper 25 times, the thickness is almost a quarter of a mile. 30 times, the thickness reaches 6.5 miles, which is about the average height that planes fly. 40 times, the thickness is nearly 7,000 miles, or the average GPS satellite's orbit. 48 times, the thickness is way over 1 million miles. Now, if you think that the distance between the Earth and the Moon is less than 250,000 miles, then starting with a piece of Bible paper and folding it 45 times, we get to the moon. And if we double it one more time.
Amir. Hello.
Yes, sir.
This is a very simple kind of question. So you take these many 45 folds to reach the moon. How many folds you'll require to go and come back? Answer in the chat box. You require 45 folds to go from Earth to the moon. How many folds you require to go and come back both?
Yeah. There are participants, 6 participants who have said 46.
Good. So
7, 8, 9, yeah, 46. Most of the answers are 46.
Good. So that is 46. So that is the power of the exponential function, a very dramatic visualization of it, and we can relate it with our exponential growth. Basically, this is a model used for, I will not show you more. Let me just give you a glimpse of some of the other things that I wanted to show. Probably we'll do one more thing, cutting a big tree. If you want to cut a big tree, there could be a problem, right? Many things can go wrong. So here is something, if you want to cut a big tree, how the things can go wrong. So cutting a big tree is not an easy job. You have to do a lot of mathematics. There is mathematics involved in it. You have to measure the height of the tree. You require some way of measuring the height. Then to cut a tree properly, you have to do some mathematics. You have to make what is called a notch on one side of the tree, and you have to make a cut up to the notch at some angle, and this angle should be 60 to 30 degrees and so on. And all this leads to, then you cut the tree. Okay, then you put this hinge and the tree tilts in that direction because there is already a cut here. So let me not go into this, which is described. Okay, let me go over to something, one more illustration before I can. Let me skip this illustration also, which is interesting. So here is something which is my favorite. So spot cricket, math in the cricket field, because cricket is one of the most loved games. So here is, I want you to look at the small clip.
It's working, put on the onside for a couple of runs. That will get 3. So we'll keep the strike. Chandrapal, it's 2 or 3 for 3.
Yes, can you, probably this is the right time, Amya, to ask for feedback. What kind of questions you can ask based on this clip? So write in your chat box, the participant. If you want, I will play the clip again. In the meantime, you can think about the possible, of course, mathematical questions that you can ask.
Nicely played. It's working, put on the onside for a couple of runs. That will get 3. So we'll keep the strike. Chandrapal, it's 2 or 3 for 3.
Right. So,
Yes, sir.
yeah.
There are like observations like we need to hit the ball, and the trajectory would be a parabola.
Good. That's good.
The other person says at what speed and angle did the fielder run to intercept the ball?
Yes.
The Duckworth-Lewis method. The path of the ball after the fielder throws it back.
Yes.
The velocity at which the ball moved.
Right.
The angle at which the batsman hits the ball.
Yes.
Consideration of acceleration and air resistance into it.
Good. So, so let me, I think, take off from this point. You see, when I showed you a clip which was dynamic, that means there was a movement in the clip, right?
Nicely played.
So your questions are all towards the movements. Now let me freeze the video at one particular shot. So I have frozen it. Now forget the video now. Supposing I show you only this part of this clip, that is a frozen clip, frozen shot of the clip. Now let me ask the same question, or let me wonder what are the mathematical questions you can ask by looking at this picture now. Now there is no clip, it is a picture. So the questions should be related to this part of the picture. So once again, in the chat box, write something.
Yeah, the responses, the first one which we got was the angle of the painting of the Airtel ad.
Okay.
Next is the angle at which the batsman is squatting.
Angle at which the batsman is scoring.
Squatting, yeah. And at what speed, what is the speed at which they are running?
Okay.
At what speed did the ball go to the fielder?
Yeah.
Then the match behind run rates.
Right. Okay. That is probably visible on the screen, something about run rate. Okay, good. So let me take this feedback. Now, you see, there is no dynamics on the screen. So saying that the fielder is running, it looks like he may be running, he may not be running. He may be doing an acting of running. We don't know that, right? There is no ball visible. So I don't know whether the batsman is hitting the ball or not. Okay. and maybe there is some data on the screen visible 200 for 3, so probably there are no number of overs given, so run rate calculating seems data doesn't seem to be enough. The only one question, that was the first one, what was the angle of the Airtel, you were saying, Amia?
Yes, sir. The Airtel ad.
Yeah, so now what is the angle of the Airtel? That seems a bit of relevant question in the sense that it looks to us that the Airtel sign is standing at some angle and is casting a shadow or something from the sun, which actually is not. Okay? This Airtel sign is painted on the ground. It is painted on the ground. There is no angle at all at which it is standing or something. So here is the question. If I want to make an Airtel sign look as it is shown in the picture, here it should look like perfectly nicely standing kind of thing with Airtel written nicely on it. What way I should paint it on the ground so that when the camera looks at it, it looks like very nice. So I hope my question is clear to you all. On the cricket ground, one does not paint this picture as it is. A deformation has to be done for this picture and painted on the ground so that when the camera looks at it, it looks very good. So if you don't believe me, let me just play the part of the clip. You will see that at some point the ball is running over this advertisement, and what does it look like?
Put on the onside for a couple of runs, but we'll get 3. So we'll keep the strike. Chandrapal, it's 2 or 3 for 3.
I think it was in the beginning, so let me probably shift it back when the ball was hit. It is somewhere here. Yes. Now here is the ad. You see? Now the camera is looking at the player, not looking at the ad. Even if the camera is looking at the ad will not. This is that Airtel ad. It looks horrible. It does not look like Airtel at all. So it depends upon at what angle the camera is looking at that ad and what is the height of that camera so that it looks perfect. Now the question that I'm asking is the following. This is what is painted on the ground is not the actual picture. Some deformation has taken place and painted on the ground, and when the camera looks at it from a particular angle, it looks very nice. So the question is, what is that deformation that should be done to look at, make it look nice? So in the chat box, if you can put some thoughts about it, if the question is quite clear to you all, that I want to paint something on the ground so that when I see it from a particular angle by a particular direction, so this ad, when I look at, when a second camera picks it up, it looks like this. So the position of the two cameras are different, of course, but to make it look really nice like this, from this angle by this camera, what should be the real picture on the ground? So that is the question.
Yeah. So there's a response which says that it's a 2D painting with using perspective to develop a 3D looking image.
Right.
And the same person, it's a 2D painting using perspective to develop a 3D looking image, and all the sides are converging at one point.
Okay.
And there's one participant who says that the shadow should be a trapezoid, and smaller at the bottom, larger at the top.
Right.
Are the responses.
So, so let me now make it more precise. Supposing you are given a problem after finishing your education, you have joined a design cell in an advertising firm, and you say, you know, a lot of mathematics and I can solve the problems. So the problem comes, how do you design this? So they say, this is the final picture I want you to make it look like. So let me make the problem slightly more simpler. So here is the picture of a smiley, perfectly circular picture. I want to paint it on the, so what deformation I should do with this to paint it on the ground? So now, saying that it is a perspective, converging and all that, that is okay. What is the mathematics involved in it? Okay.
Yes, sir.
Yes. So feedback, something you want to say that, okay, this is the mathematics used in, I will deform this. Forget about the eyes also for that. Think of a circle. I want to paint a deformed part of a circle on the ground so that when I see it at a particular angle, at particular height, it should look like a circle. So what is a deformed picture I should paint on the ground? So feedback in the chat box. Now it's a very, very simplified problem, right? I mean, as soon as you see one response, please let me know so that I can go ahead.
Yes, sir. We're just waiting for the response.
Good, good. You see, when problems are simplified, they become difficult to come to analyze and answer, right? This is the crux of the problem. Okay, so here is a hint I will be giving you. See, normally when in the morning when you are having a cup of tea, you are reading a newspaper, right? When the newspaper is lying flat on that table and you are trying to read, sometimes you are not able to read the newspaper very nicely, right? Then what you do, you lift one side of the top of the newspaper slightly up. Instead of flat, you raise it a bit and then you are able to read it nicely. I hope you are getting my hint. Is lying flat, you are not able to read, then what you do is you raise the top end a bit. So
Hello?
that, yes.
Yes, sir, you can project it from a diagonal plane onto a horizontal plane.
Okay, that still looks a bit complicated to me. But let me, I gave you see, the idea of perspective is a very good one. But how do you use it here? The idea is, see, light travels in a straight line and you are able to see everything nicely in a good perspective when the light hits that object at 90 degrees. So what I will do is, I will take this circle and try to simulate the problem. So what does the simulation mean? I will draw on a piece of paper a circle. This is how I simulate. So take a printout of the picture, keep it near a wall in a room, in this, for example, classroom. Observe the picture from the other part of the room. So go at a distance. You are standing at a distance and looking at the picture which is lying on the floor of a perfectly good circle. Now you will see, you don't see the circle. You will see it as, can somebody guess? Name the,
Ellipse.
you will see it as a, it is related to ellipse. Good. It will look like an ellipse. It doesn't look like a circle. So if you want to see it as a circle, you have to paint a ellipse on the ground, not a circle. But ellipse has to be deformed in a particular way, right? So whether that from the top you deform it at the bottom or deform it from the sides, right? So that you have to understand that, okay? So here is it in GeoGebra. I have tried to simulate this problem in GeoGebra and let us see. That will give you the mathematics also involved in doing this. This is GeoGebra. So this is a cricket ground, right? And here is the, at this point where my mouse is hovering on the left side on the y-axis near 25 is the camera. So camera is at an angle, it is at a height, taking the pictures of it, right? And I want this BC is a line. So I'm taking a very simple thing. This is BC is a line of particular height, particular height. I want, when I view this, it should look like actual BC. So here, if the perspective is 90 degrees, it will look very nice. But if it is not, then the light ray will hit C and go to F, right? So to look at BC like a BC, that actual picture, I should paint BF on the ground. So on the ground, what should be painted is the line BF. And when it is viewed from that angle, it will look like BC. So this is a very simple similarity problem in the ratio of this, what I want actual, and this is the ratio of what it should be painted. So this BC divided by BF is equal to this height divided by this. The simple similarity condition that if two triangles are similar, then the sides must be proportional. So I would strongly suggest that please do this as a actual problem in your school when actual physical meetings start taking place in the classrooms. Go to the ground and try to elongate a circle and see whether at a particular, from the second floor or the third floor, you can see it a circle or not. So this is a very simple problem that we see it every day and can be analyzed mathematically. So I think it's only 10 minutes are left. Amia, if you think there are some questions audience will like to ask, I will come to the camera view and you can ask questions if you want to ask something, and I will try to.
Sir, I have a question.
Yeah, whether Amia, you would like now, you would like to pass on the mic and ask people, whichever way is convenient. For me, it's okay.
Yes, Gomesh, can you continue with your question?
Yeah. So my question is, you said that if we do 46 folds of the paper, it can reach the moon. So how many papers do we need?
See, there was in mathematical modeling, there are always something called assumptions made. So assumption in that paper folding thing is that that paper is such that you can fold it any number of times you like. Okay, so that is the assumption made. And
Excuse me, sir. I have a question related to the paper thing.
Question is related to the paper you are saying, right?
Yeah. So,
Brin, just 1 minute.
Yeah, so let me finish that question answer so that
Yeah.
surprise you or not. What I am saying is, the assumption made is we have a paper which can be folded any number of times you like it. It can be folded 6 times, 100 times, and so on. And physically, it is not possible. So that is the difference between the actual problem and the mathematical model. Okay. Yeah. So does it satisfy your answer?
Yes. Brent, you can.
yeah. But so how would like as it like theoretically you can like fold it 100 times and all. So like, but it can't but my question is like, how can you like fold it 100 times, because like the surface area of the, because of the surface area of the paper, it won't be so much that you can just fold it for eternity.
So what is your name?
Brand.
Yeah, Brent. Let me just, I said we are assuming, you are assuming, there is a mathematical assumption to get rid of the physical constraint, that you have a paper which is big enough and can be folded as many times as you like it. With that assumption, you are proceeding. Okay. Okay. Let me give you a similar illustration. Okay. Now, have you heard about the person who invented chess? Okay. Person who invented chess, there is a story that he was a king was bored of fighting wars. He said, anybody who can give me some game which will satisfy my hunger for wars, and but I can do it at home itself. So the person invented chess and brought it to him. The king was very happy and said, I want to give you an award for this game. So what would you like to have it? He said, sir, I don't have, my aim is very modest, but he was a modest mathematician. He said, "Sir, this chess piece has got 64 squares. In the first square, put 1 grain of rice. I want rice for my eating, so put 1 grain of rice. In the next box, double it and put 2 grains of rice. In the next one, double it again. So with the formula, fill up all the 64 grains with rice. That much rice you give me, I'll be happy. My reward will be there. And now this is a problem for you. Try to do it in Excel and see how much rice is required to fill all 64 squares of the chessboard with the assumption 1 grain of rice. The first one, and next one it should be double it. Next one it should be double. And here is no folding of paper. Only you need rice, and find out how much rice is required, and let your teacher know that much rice you can purchase or not from all the markets in the world. Okay, so there is a. I'm trying to tell you that this is a reality that you have to understand, that mathematical modeling and actual scenario, there is a difference between the two. Mathematical modeling will have approximations, will have assumptions made to make it mathematical and solve it mathematically. It may not exactly fit the physical model, but it will give you insights into the physical model. For example, growing your money, you cannot do it infinitely. There are not infinite number of days. Your life is fixed. Number of days you can live is fixed. So you can only have a fixed rate of interest for a fixed number of days. Your money will grow only finite number of times. But it says if n is very, very large, then what will be the money you will grow to? Right? So n going to infinity gives you a way of approximating for n very, very large. There is a mathematical advantage of modeling, mathematical modeling. Yeah, Amya, any more questions?
Yes, sir. In the chat, there is again one more comment which I would like to bring to your notice, which says that if you want to fold the paper that many times, someone has said that the paper has to be really big. But I think I have read somewhere that you cannot fold the paper more than 8 times.
Yeah, that again, it is related to the physical constraint. So physical constraint, there is probably not big enough a paper. Probably because of the physical attributes, you cannot fold a paper more than 4 or 5 times. Maybe, but mathematically you can. You can put an assumption mathematically. What I'm saying is, in your mathematical world, to bring the problem from the real world to the mathematical world, you have to put some assumptions. Okay. Now, for example, let me give you another simple problem. Okay, which you'll probably understand. Supposing you you are traveling on a highway and you find a sign saying don't go beyond 40, don't go beyond 60. How do you think those people put up those signs on the road? Not because somebody has just sweet will that, okay, this road looks very nice and smooth and straight, so I can put, people can go at any speed they like. Okay, and somewhere there is probably a turn, so they should slow down. So such naive things don't work. You have to take into consideration many things. How much traffic is there on that road, whether it is a heavy traffic or a big trucks are going to ply on this, what is the length of the traffic, what is the weight of the traffic. In case there is an emergency, the vehicle has to stop. What is the stopping time required for that? What is the minimum distance between the two cars should we have? And there are so many things required, right, for a mathematical modeling. So I can understand that your stage probably you are stuck with physical world and the real mathematical world. Real world and the mathematical world. Mathematical world, you can make assumptions which may not be really possible, but still get solutions which will give you some insights. And this is happening at present, analyzing the coronavirus. Okay. Assumptions are made. If this is the rate of recovering, if this is the rate at which people are falling ill, this is the rate at which people are dying, and if this much medicine is available, how much more cases will come up, right? These are all assumptions made, and then conclusions are drawn. So there is a big difference between real world and mathematical world. Yes, and these assumptions, physical constraints, physical things make you constrained so that you can solve a mathematical problem. If you just take, you can't fold the paper more than 10 times. So I cannot solve the problem of folding a paper and reaching the moon. If I make the assumption, I can. Yes. Any more questions? I think there is a probably, Amia, probably when you do a bit of math modeling, as and when you do it, probably this is a input for you that you should try to say something about assumptions made to make a mathematical model work.
Right, sir.
Yeah. More questions?
Any other questions from any of the participants?
Well, I think you can always have opportunity later on to talk to me, talk to your teacher. So thank you very much for coming and asking these questions. And I hope that I have ignited some fire in your mind, and there is a dry wood in your mind which will start burning and asking questions. That is what a teacher should be doing. A teacher should ignite the fire and let the fire start burning in your mind. Whether you go to Google, you go to Amia, you go to some other teacher, read a book, try to satisfy your curiosity by asking more and more questions about mathematical things. Why this is made? Why this assumption is made? Can it not work without it? Right? How it is made? Can I write a proof of that? So these are the things we should analyze. Thank you very much. All the best. Take care.
Thank you, sir.
Thank you, sir. Thank you
Bye,
so
sir.
much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you,
Thank you,
sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Yes.
Yes, I am closing it up. Okay.
Yes, sir. Thank you so much, sir.
Okay. Bye.
I think we can all log out.